Hi, this is my first lecture in module called model adequacy checking. In this model, here first I will describe the problem, what is model adequacy checking. What we do in simple linear regression or in the multiple linear regression, we make some basic assumptions on error. For example, we assume that the error has 0 mean, and also we assume that the error term has constant variance, and the errors are uncorrelated, and also we assume that the errors are normally distributed. And okay, let me just write the things formally. Recall the simple linear regression. The model here is y equal to beta naught plus beta 1 x plus epsilon, and for the ith observation just we put I here for I equal to 1 to n. And for the multiple linear regression, y I equal to beta naught plus beta 1 x I 1 plus beta k minus 1 x I k minus 1 plus epsilon I. Okay, so this is a multiple linear regression model with k minus 1 regressor variables. So, the basic assumptions here are expectation of E I is equal to 0, variance of E I, that is the error terms epsilon has constant variance. The variance of epsilon I is equal to sigma square. Errors are uncorrelated, and also we assume that the errors are normally distributed. Okay, so altogether I can write that epsilon I follows normal with mean 0 and variance sigma square, and they are independent and identically distributed. Okay. So, today what we will do is that in this module basically what we will do is that we will present several techniques to check these basic assumptions on error, whether they are correct or not. So, gross violation from these assumptions may yield a model which is very unstable, right. So, in this module we will learn how to given a set of data, whether the data set satisfy these basic assumptions or not. Okay, so, we will talk about several um, plotting of residuals. Okay. So, based on that we will check whether these assumptions are correct or not. Okay. So, the residual first you know what is the residual in simple linear regression model or multiple linear regression model. So, E I, the ith residual is equal to y I minus y I hat. So, y I is the ith observation. So, y I is an observation and y I hat is the corresponding fitted value. Okay. So, this is called the the regular residuals, and this E I, the ith regular residual, it measures the part of variability in the response variable which is not explained by the model, because E I is the difference between the original data, I mean the response value y I and the fitted value. So, the part which has not been explained by the regression model is E I. Okay. So, it is very convenient to treat this E I as the observed value of the epsilon I, because we want to test the assumption on E I, sorry assumption on epsilon I, that is the error. We assume that the epsilon I follows normal 0 sigma square and they are independent and identically distributed. So, so the observed value, I mean this residuals E I's are treated as the observed value of the errors epsilon I's. Okay. So, what we know about E I is that first of all epsilon I's are, this is some observation, you know that epsilon I's, we assume that epsilon I's are independent, but the residuals E I's are not independent. As the n residuals have only n minus k degree of freedom, because you know about this degree of freedom. All these EIs, the residuals we can't choose independently. I am talking about multiple linear regression model with k minus 1 regressors. So, there are k constraint on involving EI. So, we can't choose all the EIs the residuals independently. So, we can choose n minus k of them independently, and the remaining k EIs have to be chosen in such a way that that they satisfy those k constraint. Well, so what I said is that it is since we are trying to check whether this assumption EI follows normal 0 sigma square IID, whether this is true or not. This is IID or not, it is convenient to think of the residuals as the observed value of the errors. Okay. And plotting the residuals is an effective way to investigate how well the regression model fit the data or to check the model assumptions. Okay, so we'll learn about several residual plots in this module, and before that I just want to introduce two definitions. One is called the leverage and the influential observations, because the things are connected. Let me just first introduce what we mean by leverage point and influential observation. Okay. So, here is a scatter plot of the observation xi yi. So, suppose I have some observations xi yi, and this is the scatter plot of the given data. Now, you see the point A, this has unusual x coordinate from the rest of the observations. Okay. So, the x coordinate for this point is much larger than the x coordinate of the remaining observations. So, this is an example of a leverage point. Okay, I'll give some some numerical example for leverage point and the influential observation also. So, if a data point has unusual x coordinate, but here you note that this point is lying on the general trend of the observation. So, if you fit the given data here, the fitted model will be something like this. Okay, so, this one lies on the fitted model, fitted line. Now, I will talk about influential observation. So, again this is a scatter plot for the observation x I, y I equal to 1 to n, and the point A here is called an influential observation. You check that this point has moderately unusual x coordinate, and the y value is also unusual. Okay. So, both the x coordinate and y coordinate. So, if I say this point is say x a, y a, then both x a and y a are larger, compared, not larger, I mean their far, I mean what I want to say is that x a is different from the center of x coordinates, and similarly y a is different from the center of y coordinate. Well, so this is here a, this point A is not lying on the general trend of the data set. So, this is this is a leverage point, as well as it is not on the general trend of the data set. So, this type of observation is called influential observation, and the influential observation has noticeable impact on model coefficients. Okay, so just let me just again let me tell that what is leverage point and influential observation. So, a point is said to be leverage point if it has unusual x coordinate, but the point may lie on the general trend of the data. But in case of influential observation, a point or an observation is said to be influential observation if it has unusual x coordinate, as well as it has unusual moderately unusual y coordinate. Okay. Now again today what we will do is that we will talk about several scaled residuals. So, first I will start with the hat matrix, and then I will talk about several scaled residual. Well, the hat matrix and various types of residuals. Okay. Let me just recall the multiple linear regression model. In matrix form, we write this as y equal to x beta plus epsilon. So, y is a vector of y1 n responses, and beta is also a vector of beta naught, beta 1 up to beta k minus 1, and epsilon is a vector epsilon 1, epsilon 2 up to epsilon n. And what we assume here is that the variance of epsilon is equal to sigma square I. Okay. So, this is the base assumption we make. This is I n. Now, solution of this multiple linear regression model is, we know that beta hat is equal to x prime x inverse x prime y if x prime x is non singular. Okay. So, we know now how to this is the least square estimator of the regression coefficient x prime x inverse x prime y. So, the fitted model is y hat is equal to x beta hat, which is equal to x prime x inverse x prime y. So, just plug beta hat here, and this is equal to so this is equal to h y, say, where of course h is equal to x prime x inverse x prime. So, this matrix is called the hat matrix. So, this is called the hat matrix, because this is called hat matrix because it maps y to y hat. That is why it is called hat matrix. Anyway, so the elements of H is equal to, say, H I j, which is equal to H11, H12, H1n, H21, H22, H2n, Hn1, Hn2, Hnn. So, this is what the hat matrix, and you know how to calculate the elements of the hat matrix, because x is known, then you can compute the elements of the hat matrix H. Well, now we will talk about several properties of hat matrix. First of all, H is it can be verified that H is symmetric. That is H transpose, or H transpose is equal to H. And the second property is that the hat matrix H is idempotent. That is H square is equal to H. Well, let me prove this one. What is H square? H square is equal to H into H. My hat matrix H is equal to x prime x inverse x prime, and this is H into H. So, x prime x inverse x okay. So, this is equal to, now this will cancel out. So, this is x prime x inverse x, which is equal to H again. Okay. So, the two properties of the hat matrix is, the hat matrix is symmetric and it is also and idempotent matrix. Now, the residual, in matrix notation, the residual is equal to y minus y hat, right. So, y minus y hat is equal to y minus, now y hat, we know that y hat is equal to h y. So, h y, which can be written as I minus h into y. Okay. So, this is equal to I minus h and y is equal to x beta plus epsilon. So, this is equal to x beta minus h x beta plus I minus h epsilon. Okay. So, this is equal to x beta sorry. So, h is equal to x prime x inverse x prime x beta. So, this is h and then x beta plus I minus h epsilon. Okay. So, this one is nothing but, so this is x beta minus again x beta plus I minus h epsilon. So, this is equal to I minus h epsilon. Okay. So, what I am trying to do is that in this lecture my aim is to introduce several scaled residual. What we know till now is that we know that just the regular residual, that is EI. Okay. Now, we will talk about several scaled residual which are useful to for some purpose. Okay. So, we will talk about standardized residual, we will talk about student student residual, and also we will talk about the press residual. Okay, so for those purpose, I need to find the variance covariance matrix of the residual. So variance of epsilon I is equal to sigma square, but variance of EI we treat as the observed value of the epsilon I, but variance of EI is not sigma square. Okay, so what I am trying to do is that I am trying to find the variance of the ith residual EI. Okay, so what I have at this moment, I have I know that EI is equal to 1 minus h into epsilon I. Okay. So what I know is that E is equal to I minus h epsilon. Now I can find the variance covariance matrix, variance covariance matrix of E. So variance covariance matrix of E is a vector, right. So variance covariance matrix of E equal to I minus h sigma square I minus h. It is a very standard one, and this is equal to sigma square I minus h square. Now as H, we know that the hat matrix H is an idempotent matrix. Then you can check that if H is idempotent, then I minus H is also idempotent. So I minus H square is equal to I minus H. So this is we can write as this is equal to sigma square I minus H. So this is the variance covariance matrix of E. E is it's a vector. I hope you understand that E is E1, E2, En, and this is the variance covariance matrix of E. So from here I can write the variance of EI is then equal to sigma square 1 minus the ith diagonal element, it is 1 minus I 1 minus h I I. So, h I I is the ith diagonal element of H, okay, where h I I is the ith diagonal element of the hat matrix H. And similarly, you can find the covariance between not necessary, but just covariance of between the ith residual and the jth residual. See, EI is you can find it from here, that is equal to sigma square h I j, of course a minus here. Okay. Well, I have something to say more about this the ith diagonal element. Okay. Well, so what is HII? HII is the ith diagonal element of the hat matrix H, and the hat matrix H is equal to x, x prime x inverse x prime. So, what is this x? X is the coefficient matrix sort of. So, x has the rows x 1, x 2 prime, x n prime. So, x I prime is associated with the ith observation, right. Now, I am interested in the ith diagonal element of this hat matrix. So, I hope you understand that H I is then just x I prime x inverse x I. So, where x I prime is the ith row of X matrix. So, you can check that what HII does is that HII measures the distance of ith observation from the center of x coordinate, and you have to understand. Okay. So, this is enough to explain, this is what the HII is, that is this quantity, and the xi is the xi prime is the ith row of the X matrix, and then HII measures the distance of the ith observation from the center of X coordinate. Okay. And it is not difficult to observe, realize that HII, they are in between 0 to 1. So, what message I want to give from this HII is that you must have understood that HII is the ith diagonal element of the hat matrix H, and it measures the distance of the ith observation from the center of X coordinate. And now you recall the definition of leverage point. A leverage point is a point which has unusual X coordinate. So, it is quite obvious is that the HII is going to be large if the ith observation is a leverage point. So, somehow from HII we can get information about the leverage point. Okay. So, this is what I wanted to mention here. Next we move to some there are various type of residuals. Till now we know only one residual, that is EI, that is called the regular residual, and I will introduce 3 more scaled residuals in this lecture. Okay. The first I will talk about studentized residual. Okay. So, what is studentized residual? We define we define Ri as Ei by its standard deviation. What we know, what we did just now is that we have computed the variance of Ei. Variance of Ei is not sigma square. We know that variance of Ei is equal to sigma square into 1 minus h I, right. Now, the standard deviation of Ei is just the square root of this quantity, and since sigma square is not known, we generally estimate sigma square by ms residual. So, the studentized residual Ri is nothing but this thing ms residual into 1 minus h I. So, Ei by its the ith residual by its divided by its standard deviation. Okay. So, it is very easy to observe that studentized residuals have constant variance, that is variance of Ri is always going to be equal to 1 regardless of the location in x coordinate. Of course, when the form of the model is correct. So, this is one scale residual. Next, we will be talking about standardized residual. Okay. So, what is a standardized residuals? Standardized residual is defined by di equal to ith residual divided by just ms residual. So, what we did here is that we have just replaced we are just approximating the standard deviation of Ei. The actual standard deviation is this quantity, or actual variance is this quantity, and what we do in the standardized residual is that we approximate this quantity by sigma square. Okay. So, here we approximate ms residual as variance of ith residual Ei. Okay. So, till now we know about two scaled residual, one is standardized residual and the other one is studentized residual, and both the scaled residuals they give almost the similar information, but in some cases they are different. Okay. So, I will just give one example, this example is from a book by Montgomery. There we have the value of studentized residual and the standardized residual. We will compare and we will see when the values both those two scaled residuals are almost similar and when they are different. Okay. So, this is an example. So, this is an example from Montgomery book. Here the first column is the observation number. There are 25 observations and the second column is the delivery time, which is the response variable. The response variable is the delivery time y in minutes, and these are the values, and there are two regressors here. One is the number of cases, it is denoted by x1, and the other one is x2, which is the distance in feet. Okay. So, this is an example with this is an example of multiple linear regression model with two regressors and one response variable, and you know how to fit a multiple linear regression model to this data that we have discussed in the previous module, and here is the fitted model. Okay. Once you have the fitted model, you know the actual value of the response variable, you know the fitted value of the observation of the response variable, then you can compute, you can compute EI, which is equal to YI minus YI hat. Okay. So, I have the table for this regular residuals. Here is the table. Well, so what it says is that the first column is the number of observations, the second column is EI minus YI minus Y hat. So, the second column gives the residuals, I mean the regular residual EI. The third column gives the standardized residual EI by root of MS residual, and the fourth column gives studentized residual. Okay. Now, if we look at these observations carefully, first let me refer the previous thing. Here you can note that the ninth observation, which has unusual x coordinate. So, here the x1 value is 30, whereas the center of x1 is quite less compared to 30, and the value of the regressor x2 is 1460, which is also quite large compared to the center of x2 coordinate. Okay, so it appears that this seems to be a the ninth observation seems to be a leverage point or an influential observation. And let me check the residual for the ninth observation. Note that the residual E9, that is the residual for the ninth observation is 7.41, and which is this is suspiciously large, this residual compared to the other residuals. And also let me check the value of standardized residual for the ninth observation, that is 2.27, and the value of the studentized residual for the ninth observation is 3.21. Okay. Instead of now, what I want to make observation here. What I want to comment here, my statement is that this R9 is substantially larger than D9, whereas if you compare R8 and D8, there is no much difference. Similarly, say R7 and D7, there is not much difference between the standardized residual and the studentized residual. So, my final conclusion here, what I have observed, or what you need to know is that that the standardized residual and the studentized residual, they give almost the same information, similar information, but there will be a substantial difference between the standardized residual and the studentized residual if the observation, if the associated observation is an influential observation or leverage point. So, if the given point is the given observation is leverage point or influential point, then there will be a substantial difference between the studentized residual and the standardized residual. Otherwise, they are almost similar, and you have to understand why it is so. Just give outline of this fact. Let me just recall what is studentized residual. Studentized residual is Ri, which is equal to Ei by Ms residual into 1 minus Hii. This is the studentized residual, and standardized residual, I think it is Di. Di is equal to Ei by root over of Ms residual. Now, if the observation is an influential observation, then Hii is going to be large. So, the limit for Hii is it is between 0 to 1. If this is large, that means this is close to 1, and then this is small. The denominator is small, means the whole thing is large. Okay. So, that is why and in case of standardized residual, Hii is treated as 0 always. Okay. So, if the ith observation is an influential observation, then HII is going to be large. HII is large means 1 minus HII is small, that means the denominator is small, and then the whole thing is going to be large. So, that is why in case you can, this is one way to identify whether the observation is influential or not, looking at the difference between the studentized residual and the standardized residual. Okay, I have to stop now. Thank you.